Paulo, thank you very much for having accepted our invitation. We are looking forward to hearing your talk. The floor is yours.
Okay, thank you also for the invitation. It's a pleasure to present this work, which is very fresh and recent. The session is entitled Predictive and Prescriptive Analytics for the Design of New Textile Fabrics. I'm going to present this lecture in two parts. First, I'm going to give a brief introduction to the combination of predictive and prescriptive analytics for decision support. Actually, this has been probably one of my longest threads of research ever since I got into my PhD. I do a broad research in many different areas, mostly applied. This combination of predictive and prescriptive analytics is one of the topics that throughout the last 20 years I've been working through in somehow consistent manner. So what is AI? Nowadays, this is a catchy term. Everybody talks about AI. One way to view it is as the simple equation, which means an interaction between data and algorithms. There are many subfields within the area of AI. And what particularly interests me is when you combine some subfields of AI, namely machine learning and meteoristics, to provide decision support. So you can achieve business analytics if you use machine learning for prediction, where you get the predictive analytics part, and if you use meteoristics for optimization, where you can get the prescriptive analytics. There's also an old term of decision support systems that was proposed in the 1960s, and it has developed in many diverse subtopics as well. Some have changed through the last decades, and I'm particularly interested in decision support systems that are data-driven, meaning that produce business analytics, and if they use artificial intelligence techniques, I like to call this modern intelligent decision support systems. There have been many authors and scholars that have used the combination of prediction and optimization to support decisions. But the first author that I've seen that has explicitly stated this as an architecture for decision support was Mikhailovics in 2007. And he has written a book where he proposed this concept of adaptive business intelligence. And the idea is to have an adaptive model that's data-driven that combines prediction and optimization in order to properly assist decisions. A few years later, the famous Gartner group in 2011, 2013, they came up with this Gartner Analytic Ascendancy model, where they basically catalog the types of analytics that you can do over data in four main types. And the last two ones, which involve predictive and prescriptive analytics, are the ones of particular interest if you want to do decision support. They didn't mention the previous work of Mikhailovics, but somehow in this model, there's this notion that if you do first predictive analytics and you combine them with prescriptive analytics, then you can gain value that is helpful in many real-world application domains. So a few years later, I myself combined in a very simple way an architecture that I called TADA, which means Technology for Adaptive Data Analytics, which basically picks up the Gartner categories, the functional categories, but instantiates them with technology. So you can have a data system, a big data system that helps you to do descriptive analytics and diagnostic analytics. Machine learning can play in many of these analytics types. And there are several options for you to do prescriptive analytics, but I particularly praise and value modern optimization. And I'm going to show you a detailed example of why it's helpful. And the idea is that at the end, you provide value that is a suggestion for an action that is very close to the real world domain. So it's easy to select an action which later can affect the environment. And if it affects the environment, you can collect new data that reflects this. So you can have this adaptability aspect. I proposed this architecture when I applied for my full professor candidacy. And the only place where it appears is in the Portuguese statistical bulletin. It's a public document, and I have presented there. So this is why I mentioned it in 2021. So what can you get with predictive analytics? Basically, we mean, in most of the cases, data-driven. So you have data. In most cases, you assume that you use supervised machine learning algorithms. The algorithms, they learn an implicit function that is hidden in the data. And if the feeding or the training is well done, you can generalize some patterns or rules that are hidden in the data and perform predictions that are useful for unseen data. And then there are many techniques that can be used to do prediction. Decision trees, many types of ensembles, random forests, Shinshu boost, support vector machines, many types of neural networks, which nowadays people focus more on deep learning and so on. Actually, there are hundreds or thousands of different machine learning algorithms that can be used to achieve prediction. I also, as already said, written this book, Modern Optimization with R, which is in its second edition, was published by Springer. And in the book, I detail a lot an artificial domain that it's not well known by the public, because machine learning is now a hot topic, but it's very valuable, which is known as meta-heuristics. And the idea is there are many different search engines that use some kind of a guided search. And the guided search has a weak link with a real problem domain. And this means that these techniques, they are a kind of universal problem solvers, because you only define a representation of the solutions that you are trying to search, and then you only need a function that evaluates the quality of the solution. If you get this, which is a weak link to a very complex problem, you can apply any of these techniques. Some are more local, like simulated annealing, tableau search. Others are more global, like evolutionary computation, and they're in many forms, or particle swarm optimization, and so on. I have, in my history of research, applied this type of combination of prediction and optimization in many ways. I'm going to show very, very briefly just two different applications, and then I'm going to detail the most recent one. So a former PhD student of mine from civil engineering has applied the combination of prediction and optimization for doing a planification of earthworks which are produced for when constructing a new highway. The idea is to remove extra rocks and dirt from hills and put in the valley, so we can have a smooth driving. and there's a lot of equipment that needs to be optimized. And in short, what he did was he applied neural networks to predict the capacity of one specialized but very important machine, which would be the efficiency of a compactor, giving the terrain characteristics and the speed and other elements. And we achieved a good prediction capability using neural networks. And then we applied a multi-objective evolutionary algorithm to optimize plans, taking into consideration in a simultaneous way 2 different objectives, to reduce the duration of the earthworks and also the costs. And this has led to an interesting piece of work that received a national prize from the civil engineering domain. In a completely different work in the same year, I published a work at the EPIA, which is a conference of AI, and it received the Best Paper Award. It was held in Coimbra at that time. And the idea was to predict first the popularity of online news using a platform that is quite known in this field called Mashable. And the idea was, the question of research was, could we predict the prediction of a news before the news was published in terms of the amount of shares in Facebook, Twitter, and other social media? And using a random forest, we got a reasonable prediction binary of probability of popularity. And then once we had a model that was interesting in terms of estimating popularity, we use it as a surrogate model of reality. And then we applied a metaheuristic, which was a stochastic hill climbing algorithm, to tweak a little bit the current news, asking questions, hundreds of questions. What if? What if we reduce the text title? What if we include a new image? What if we include a new keyword that it's in the text? It has been used in previous news, but the author hasn't put it as a keyword. Would the popularity increase or not? And asking this hundreds of times to the random forest model, we have shown that for 1,000 news, we could on average increase the popularity by 15%. And it was a completely different example how to combine prediction with optimization. So this is my introduction. So let's now move to the second part, which is to present the actual recent work that we did about the predictive and prescriptive analytics for the design of new textile fabrics. This work was inserted within a larger R&D project, a 3-year funded with 9 million euros. It involved different textile companies, different research lines. I'm just going to talk about the work where I was involved, that was developed at CCG, which is interface unit that produces applied research between the university and real companies. In this particular work, the motivation is the following. So due to fashion trends, it's very common for textile companies. They have this need to constantly produce new textile fabrics. And when they need to design a fabric that they never have designed before, the typical workflow is something that as presented in this slide. So basically what they do is that they try to select the most similar fabric that they have in their database. And then the designer looks at it, uses his own intuition and experience, modifies a few features, and the goal is to meet some target physical properties, some elasticity properties, some peeling, some weight, some resistance, whatsoever. In most cases, after he produces his work and sets up a fabric design, Then there's a need to do a prototype production, which involves setting some textile machines. I'm going to show a few examples of them, and involves using many yarns and raw materials. And it's not possible to produce a prototype with just 1 centimeter. They need to produce several meters of this fabric. And then they collect samples that go to a laboratory and do some testing. And in most cases, the test reveals that the fabric is not approved. And if it's not approved, they need to repeat this process. And the company that launched this need for solving this with some kind of intelligent decision support system stated that there were some cases that they need to do this 20 times, and each time requires costs, requires time. So it's not an easy process. And the challenge was, if we use something that is data-driven, is it possible to reduce the number of prototype production attempts and designing fabrics that are more closer to the client needs? So this is the main challenge. One of the aspects that involves this domain is that there's a high number of input variables. In these images, I'm showing example of a wool yarn, but there are many other types of yarns made of nylon and other types of components. Then we need to decide which are the yarns that are going to appear in the weft and of the fabric. The fabric can have a more denser or less denser number usage of these yarns. And once the design is selected, some of the coils are manually inserted. They go into a loom machine, and then the loom machine starts to, in an automated way, to produce the fabric. There are many input variables. I'm going to show a few of them. So we need to select the yarns that are belonging to the weft, which corresponds to the horizontal yarns. We also need to define the yarns that appear in the warp, which correspond to the vertical ones. Then we need to define the distance in the vertical yarns, the horizontal yarns. We need to define how is the reed, how many picks does it have, what is the width, and so on. And in order to achieve the need of the company, we proposed, after many research iterations, we proposed this intelligent decision support system, which is data-driven. And it includes two main components, a predictive model and a prescriptive model. It also has a model related with data extraction and processing, but I won't detail it. In terms of the predictive model, we had two different prediction goals. The first one, which is the most important one, is to predict the physical properties. That is what the textile client requires and asks when he goes to a textile company. But we also identified the need to predict the fabric composition, which is an information that is very useful for users. It says, for instance, the percentage of cotton that a fabric has. And it's not trivial to compute this looking at the inputs that we have. That's why it's not an easy formula, because the yarns have different sizes, have different amounts of ways of interconnecting to the fabric. So we also define this as a prediction task. Regarding the prescriptive model, we designed first something that was required by the company, which was having a function that selects the most similar fabric, because it's the process that the designer uses, and previously this was used by kind of an Excel spreadsheet thing where it was a more visual search or by hand doing some queries, but we did this very simple using a kind of a nearest neighbors approach. And then we applied the optimization model, and the goal of the optimization model is to automatically select the set of inputs by probing a lot the physical properties prediction model. But I'm going to detail it in a while. This overall the intelligent decision support system has many ways to be used, and in the journal article we explain them. Many of them would require a subjective evaluation, having access to textile designers to understand if they found that the system is useful or not, because there are many ways to use this system instead of just running, for instance, the optimization model and picking up the best results. The textile designer could select some of the solutions from the optimization model and then probe them and then run the optimization model again and so on. So there's a lot of possibilities of interaction, but in this research we only opted to perform an objective evaluation. So we are going to measure in each of these components, the fabric, composition, prediction, the physical properties, and the optimization by computer simulation experiments that we did, but using real data, real historical data. So in terms of the textile data, all of them are related with one major textile company. Actually, it was really difficult to collect the data with enough quality due to some quality lack of standardization in the two databases that we analyzed. But at the end, after many meetings and in some cases, manual corrections of data records and attributes, we end up with a data set that includes 8,650 fabric examples. We divided these examples into subsets. One is used just for the predictive experiments, and then we randomly select 100 data records that were separated from the predictive experiments and that were used just for the prescriptive experiments. We also had a few categorical attributes like the yarn and so on. Some of these categorical attributes have a huge number of levels, thousands of levels, things like that. So in order to avoid an explosion of inputs like the one-hot encoding would lead to, we opted to apply a very simple categorical to numeric transformation, which is the IDF. And it's a very nice transformation because basically what it does is that the most common categorical levels are more spaced and more together in this numerical region, while the least common levels are closer together and put on the right extreme of the numerical scale. Basically, it does this. In terms of the design features, after several meetings and experiments, we ended up with this summary of the main attributes. Some of the attributes are numeric, some are categorical, and we use the IDF transform. In most cases, these are the inputs, but there are some special inputs that make the input space representation a little bit difficult, because the yarns have two values, the code and the number of repetitions, and there's a variable number of yarns that can appear in a fabric. Also, after the fabric is produced, it can follow a number that is variable of finishing operations like washing, cleaning, putting some color and so on. So this was an issue that we need to deal with. In terms of the outputs, we had a huge number of physical properties, but we only focused on the most common ones, which are 4: the bias distortion, the elasticity on the warp, on the weft, and the peeling. And in terms of the final textile composition, we had more than 95 different classes of fabrics. So instead of doing this as a heavy multi-class classification problem, we transformed it into a regression task, which has the same structure of the physical properties, where we try to predict the percentage of the 6 main components that can appear in the final composition, like the percentage of cotton and so on. So going on to the predictive modeling, where we use the machine learning, we attempted to produce 2 different goals: the physical property prediction and the textile composition. Both goals have the same number of inputs. In order to achieve a robust evaluation, we did an external tenfold cross-validation, and we opted to use 44 inputs. The way we represent the inputs, it's not trivial due to the how should we use the yarns and the finishing operations, but we ended up using a reasonable solution that uses up to 6 yarns for the raw warp and 6 yarns for the weft. This means that we can represent around 90% of the fabrics. If a fabric only has 3 yarns, then we use a 0 padding, so we include zeros. If it has more, we ignore them. So this is how we use it, the yarns. Regarding the finishing operations, we used a similar strategy. We used up to 10 a sequence of 10 different finishing operations. Each operation is a categorical value that we transform with the IDF. So once we fixed the number of inputs, for each of the 2 predictive tasks, we applied 2 different modeling approaches. One is in terms of for each of the regression tasks, we have diverse set of outputs. So in the case of the physical properties, we need to predict 4 different outputs. In the final textile composition, we need to predict 6. So one option is to use a single target regression approach, which means we use a machine learning for each output. So in the case of the physical properties, we need to model 4 different prediction machine learning models. We also attempt a different approach, which is just use a single model and use multiple outputs. We call this, and it's known in the literature as a multi-target regression. For the single target regression, we used an automated machine learning tool, which was based on the H2O, which is open source, and it has provided some interesting results in another paper where we compared 8 different automated machine learning tools. And the advantage that we gain by using this AutoML is that it automatically performs a competition of 6 different machine learning models, including random forest, boost, and stacked ensembles. So we don't need to manually configure the learning algorithm and its hyperparameters. We just push we just execute one function, which means like pushing a button, and we get automatically the model, one for each of the targets that we are analyzing. The idea of the multi-target regression, we could have tested other specialized algorithms, but we used basically a model that is very natural for doing multi-target regression, which is a neural network. And we use the deep learning multi-layer perception with several hidden layers. And in the case of the physical properties, the network has 4 outputs. In the case of the final textile composition, it has 6, something like that. Going on to the prescriptive modeling, where we apply the optimization. We did a lot of initial experiments trying to get interesting set of inputs. So the challenge is we have 44 potential inputs. All of these 44 values define a fabric. And we need to get the best set of these 44 values, which is our search space. And it's not easy to get these best values because there are different combinations that can produce the same physical property predictions. So we had ended up with an elegant solution that I haven't seen this in other works. Probably there are some that have done this, but I wasn't aware of that. And the elegant solution assumes a bi-objective optimization. So we simultaneously try to minimize two errors. One, which is the most natural one, is basically to reduce the error between the predictions. So if we have a candidate solution S, which means a combination of 44 input values within our space, we get the predictions from the best predictive model that we are going to use as a surrogate model of reality. Instead of building a prototype, we just query in real time the machine learning model. And we compute the absolute difference between the desired properties and the predictions. So the smaller the error, the better are the fabric properties that meet the client needs. But we also simultaneously have designed the second goal, which has the same importance as the previous one. And the idea here is to try to minimize the distance of the S values from what the learning model knows. And what the learning model knows basically is the training set. It was trained using the training set. So the idea is that we want to minimize the Euclidean distance of S minus one example, which is the minimum distance that belongs to the training data set. And then we divide it by the square root of the number of inputs, so that both measures, they are normalized within 0 to 1. Why do we want to minimize the input distance? Because of two main reasons. First, the optimization algorithm is blind. It doesn't know nothing about reality. It just queries a solution S, and if it gets a good predictions, it says it's good. But some of the input combinations, they were strange or impossible to achieve because there are many restrictions. We cannot use all types of combinations of yarns. Only some types that make sense. And the amount of rules is very large, and the company couldn't even explicitly provide us the full set of rules that allows to build feasible fabrics. So this is one reason. So if we minimize the distance to the training set, then we have a set of S values that is very close to something that they have produced in the past. The other reason is that we want to have trustable predictions, because you can prove, or using cross-validation whatsoever, an estimate of the generalization capability, but that means that the predictive model is good at predicting values for what he knows, the learned space. But we want to interpolate rather than to extrapolate. So if we do predictions for some input space that was never used in the training set, then probably the predictions, they are not meaningful because the model has never learned what to do in that region. So that's why we put these two forces to get what the client needs, but also to get some input values that are closer to what would make sense in reality. Since we want to simultaneously reduce these two objectives, we applied a multi-objective method. Namely, we used evolutionary optimization algorithms, and we compared two approaches, two algorithms, NSGI2 and RNSGI2. So going on to results, what we have found in a consistent way is that the single target regression always produces the best results. So the best results are in bold. This is the average absolute error. This is the normalized absolute error. And for all four properties, in a systematic way, the single target regression produced better results than the multi-target regression. So we opted to use the single target regression. Just to show you a few examples of the quality of the predictions, for some properties, we achieved a very good quality, like the elasticity warp and the elasticity weft. The predictions are the blue points, and they are very close to the dashed dark line, which means the perfect prediction. So if you predict a 20 of elasticity and reality is exactly 20, you are having a very good ideal prediction. Going on to the textile composition, we also observed the same phenomenon. The single target regression produces better results than the multi-target one. These are the absolute mean values, which are very small, very close to zero, for all 6 types of fibers. So this is why we selected the single target regression. And we also did an extra analysis, because since the single target regression produces an individual model for each of the fiber types, it doesn't assure that the sum of all percentages is equal to 1. So we combined 2 extra functions, post-processing functions, to guarantee that the sum is 100%. One is the simple proportional sum. So we sum all of the predictions and divide by, assure that the division by the sum is always 100%. And we also applied the softmax function, which does the same, but using some exponential functions. And in this table, we show that there's a slight advantage of using the proportional post-processing function. T means a tolerance. So using very small tolerance of 0.01% up to 10%, what this the values that present in this table, what they show are the classification accuracy. How many fabrics can we correctly predict the full textile composition? Imagine if it's 95% cotton and 5% nylon. If under 1% error, if our method predicts 94% cotton and 6% nylon, then it would be correct, else it will be wrong. So we can see that using very small tolerance, there's a high accuracy, and in some cases, for some tolerance values, the post-processing function slightly produces better results. That's why we have selected this option. Going on to the prescriptive modeling, we have monitored the evolution of the 2 optimization algorithms. In this table, the lower the results, the better. It's not easy to show results because we are simultaneously optimizing 2 different objectives. But one way to condense the 2 different objectives in a single measure is to use what is called the hypervolume. And in these 2 graphs, we can see that the blue hypervolume tends to be higher during the execution of the different optimization iterations in comparison to the NSGA2 standard optimization algorithm. So statistically, for 100 different fabrics, we have shown that the NSGA2 tends to produce better results. in this table, we detail other dimensions for comparing the two optimization algorithms. We have compute for the Pareto curve, which is which I'm going to show in a while, but it's the result of this algorithm. It doesn't show at the end just one solution, but it shows a set of solutions called the Pareto curve, and each solution is non-dominant, meaning that it's better in some of the functions than the other point. So looking at this Pareto curve returned by the two algorithms, we have computed the median, the mean, the amount of time that was required by the algorithm, and the number of solutions that appear at the end in the Pareto curve. And what occurs is that for R and SGA2, it has a richer set of solutions, so the user can select better different trade-offs. But more interestingly is that it tends to produce a lower distance and a lower predictive error with statistical significance. Probably it's easier to show with two particular examples for two fabrics. So we want to minimize in both these graphs the input distance and the predictive error. And the RNSGA2 is an algorithm that needs the user in advance to set some reference points. And we selected two reference points, which are these two stars that are very close to the ideal 0, 0 value. And these two stars kind of serves as a guide to push the Pareto points closer to a region that is near to each of these reference points. What the two examples show is that at the end, the final result, which is this blue Pareto curve and this black Pareto curve, we can see that RNSGA consistently has obtained a richer Pareto curve with more data points and that are more closer to the ideal region. In these two graphs, we show for the selected algorithm, the RNSGA2, and for the same two selected fabrics, how the evolution occurs. So initially, most of the data points, they are set randomly. We don't use any domain knowledge information. We could have used, for instance, a seeding technique where we could select first the most similar fabric and input it into the initial population. But we haven't done this on purpose, just to perform what we mentioned, the objective evaluation. Using this blind system, could we or not achieve good results? That was the challenge. So in this case, the light gray points belong to the first generation of the optimization. And as the process proceeds, the points get darker and darker until the end. So this is a kind of a graph that shows in a nice way how the conversion of the optimization algorithm, which performs a simultaneous minimization of the input distance and the predictive error, how does it occur? And at the end, it returns this Pareto curve. And it's up for the designer looking at the final Pareto curve if it prefers a solution, because each dot is a set of 44 values that produces a fabric. Some have a lower predictive error, like these points, but they are more distant from what is known in terms of history. Others have a higher predictive error, but are more close to what's recorded in the Textile company database. So it's something that the user could decide. So just to conclude, what we have shown in this research is that we have modeled a complex task that is non-trivial, and we have shown that the combination of predictive and prescriptive analytics can produce an interesting value for design of new textile fabrics. The main conclusions in terms of results is that the single target as performed by the automated machine learning approach provided the best results for the two predictive tasks. And in general, we achieved high quality predictions, or translated with a low error. We achieved an error of 4% for one of the properties, and the highest error was 11% for the peeling. In terms of the textile composition accuracy, we achieved a high value, 80%, if we assume a very small tolerance of just 1% of deviation in any of the 6 main type of fibers. As for the prescriptive results, which use the AutoML single target regression approach, the best results were achieved using the RNSGR2 evolutionary multi-objective method, and it tends to select at the end predator curves that are associated with an average of 11% predictive error and 6% distance. We did not apply this full decision support system in the real environment because it was very difficult within the 3-year time frame to extract the data, to understand actually what was the requirement of the textile company and produce the predictive models. So this means that we haven't actually evaluated the true capability of this system to reduce the number of prototype attempts, but we believe there's a strong potential for achieving this. Another interesting future work is that there are other industries that have similar requirement as the textile sector. For instance, the plastic and the chemical industries, they often need to build new recipes of products with new properties, and they also produce prototypes and productions and so on. So a similar strategy could be applied there. In terms of the research outcomes, we managed to have a prototype running in the textile company. It only performs the prediction part. It was the thing that we achieved within the 3-year time frame, but it's working in the textile company. And we have published very recent, accepted in April this year, a research article in the journal Neural Computing and Applications. And this research also served as the basis for a PhD thesis that was defended by Rui Ribeiro in March 2023. So I ended up this talk. I hope you find it useful. If you have any questions, I can answer. And thank you.